As you can see, the objective in this video is that students will be able to find the area under a curve using trapezoids. So we're going to continue our discussion of evaluating definite integrals geometrically. We've looked at that counting blocks. We've looked at that by using Riemann sums, and in this video we're going to take a look at using trapezoids to accomplish exactly the same thing. If you are not in my class, you may want to skip over this warm-up. If you are in my class, stop the video, do the warm-up, and then resume and see how you did in the warm-up. This is page 18 in your packet. Problem number 1, you've been given dv/dt, so you know from prior discussions that I'm giving you the acceleration of a particle to be negative 9.8 meters per second squared. Your job is to determine the velocity 5 seconds after an object is dropped from the top of a building. So first of all, we're going to need that velocity function if we're going to calculate the velocity. So I'm going to find the antiderivative of negative 9.8 dt, which will give me negative 9.8 t plus c. That is my velocity function. And it's a general solution, so I need to use the information given. They told me that at 2 seconds the velocity is negative 12, so I'm going to use that to solve for c. So when I do that, that will give me negative 12 is equal to negative 9.8 times 2 plus c, which will give me a c value. If you calculate that, c is equal to 7.6. So the particular velocity function is negative 9.8 t plus 7.6. And then I want to evaluate that at 5 seconds. So v of 5 is negative 9.8 times 5 plus 7.6, which gives me negative 41.4. What are my units here? Meters per second. So we know because the velocity is negative that the object is still falling at a speed of 41.4 meters per second. Number 2, if the initial height of the building is 20 meters, so in this case they're telling me that position at time 0 is 20, determine the particular position function. So we're going to find the antiderivative of the velocity function that we found in the last problem, which would give me negative 4.9 t squared, just using the power rule, reversing that, plus 7.6 t plus c. And when I substitute 0 for t and set that equal to 20, my position function turns out to be negative 4.9 t squared plus 7.6 t plus 20. And again, all I did was substitute 0 in place of t and set the position function equal to 20. And that's my particular position function that represents this particle movement. Number 3, if the object hits the ground at approximately 1.389 seconds, what's the acceleration at that time? Well, hopefully you figured out when you did this that there was a little bit of a trick question. The acceleration is constant regardless of the time, so that would be negative 9.8 meters per second squared. Doesn't matter the time. And then finally, number 4 is a review of what you were doing in your homework last night and what we talked about in the last video. F of x is a continuous function. We have selected values in the table. We want to approximate the area from 1 to 8 using 4 subintervals, a left endpoint approximation. So we're using Riemann sums like we talked about yesterday. Now, I gave you this problem in particular because notice that the interval is from 1 to 8, and I gave you an extra data point that students often try to somehow get in there because they're not reading carefully. That 0 to 4 is a distractor data point, and we don't use it in this particular problem. we said we're going to put in 4 subintervals. So the first rectangle, rectangle number 1, goes from 1 to 3. Rectangle number 2 is from 3 to 6. Rectangle number 3 is from 6 to 6.6. And rectangle number 4 is 6.6 to 8. And again, we have another extra data point, at least for this particular problem. Okay, so rectangle number 1. Now, another thing you notice is that the width of this rectangle is 3 minus 1 is 2. The width here is 3, so we don't have the widths in common anymore. The width is 0.6, and then the width is 1.4. Now, this is a left endpoint approximation. So, if it's a left endpoint approximation, the last endpoint does not determine a height. Remember, we get the heights out of the y values, and it's determined by what kind of approximation we're doing. So the height of the first rectangle, so that I'll call it h for height number 1, height number 2 of the second rectangle, height number 3 of the third rectangle, height number 4 of the fourth rectangle. And these rectangles have to be calculated independently because we don't have a common width. So we have 2 times height number 1, 3. That takes care of rectangle number 1. Then we have a width of 3 multiplied by height number 2, which is 3. That takes care of rectangle number 2. Then we have a width of 0.6 multiplied by height number 3, which is 1. And then we have a width of 1.4 for the fourth rectangle multiplied by height number 4, which is 5. And if you calculate that, that'll give you 6 plus 9 plus 0.6 plus 7. So 6 and 9 is 15, and 7 is 22. If I calculated correctly, 22.6. If I made a miscalculation, please forgive me, and you can let me know at another time. And then the last thing that I'm asking you to do here is to approximate the derivative of f at 7. This is kind of a review as we start heading back towards the exam. We have a table of values. Notice that the number 7 is in between 6 and, it's in between 6.6 and 8. So there's a 7 somewhere in between here. So my approximation of the derivative, again, it's an approximation, I don't know how good it is to do change in y over change in x. So I'm going to use this data point and this data point. Change in y, 8 minus 5, over change in x, 8 minus 6.6, which is 3 over 1.4, and you could simplify that. But I just want you to remember, when you have that data, we're going to use the approximation strategy of going one data value above and one data value below to approximate the instant rate of change. So we're using average rate of change to approximate instant rate of change. All right, let's move on to what we're going to discuss, the big idea in this video, some things that... And we, as I said earlier, we're going to continue evaluating definite integrals. You can see that here, definite integrals, which is area under a curve. We're going to do it geometrically. We've already done that geometrically by counting blocks. That's how we started out our discussion of the area, and we did that using Riemann sums. And now we're going to look at another geometric shape, which is the trapezoidal rule. And this is not going to be a big stretch for you. It's the exact same thing that we did with rectangles, except we're using trapezoids instead. So let's take a look in this problem. We have elevator Doris' daughter, driving in her rocket ship at time t equal to 0. She fires her rocket engine. The ship speeds up for a while, then slows down as Aldrin's gravity takes effect. The graph of velocity, so again, here we go with our velocity, and it's measured in miles per minute, and this is minutes. Take some time to read the problem yourself if you're in my class before you completely play through the video. Try to think through it yourself and figure it out. Then resume the video. What math concept would be used to estimate Ella's distance from 0 to 8? Well, we're going to accumulate the area from 0 to 8, v of t dt. We're going to use that to approximate how far Ella travels. And in this case, that would be how many miles that she travels. Estimate the distance in problem 1 geometrically. We could count blocks. We could use Riemann sums. We're going to go straight to the point, and we're going to do trapezoids. We're going to use 6 trapezoids. No, we're not. Are we going? Yeah, we're going from 0 to 8, so we're going to use 8 trapezoids. Sorry about that. I mean, we could use 6 trapezoids. We could use as many as we want to or as few as we want to. The more, the better. But for simplicity's sake, I don't really want to deal with all the fractions right now. That's going to be coming. But we're going to use 8 trapezoids just to keep our work kind of simple here. Now, when you're drawing the trapezoids, all you're going to do is you're going to draw slices. So 0. Notice I'm drawing all the way to the curve. 1, 2, really easy. 3, hopefully I'm hitting these. 4, 5, 6, 7, 8. Okay, let's clean up the bottoms a little bit. When you draw the trapezoids, all you got to do is connect the tops. So there is a trapezoid, a trapezoid, a trapezoid, a trapezoid, a trapezoid, a trapezoid, and a trapezoid. Take time and make yours a little, well, one more, look a little bit better than mine. And the nice thing, I think you can see right away, the nice thing about trapezoids is because the tops are going to be slanted, they oftentimes better approximate the curve. So we're doing the same thing that we've been doing. We're approximating that area, but we're using trapezoids. So let's review some geometry here. To find the area of a trapezoid from geometry, it's 1/2 of the height times base 1 plus base 2. Now let's extend that. For us, we're going to think of it as 1/2 of the height times the sum of the bases, because we have multiple trapezoids. In this particular problem, well, first of all, let's pull out one trapezoid. I'm going to highlight the first trapezoid, this one right here. If I pull that trapezoid out, this is what, let me give myself a little more paper here. This is what the trapezoid looks like if I pull that first trapezoid out. So what I want you to see about that is that these are the parallel sides. So this would be base number 1, this is base number 2, and this is the height of the trapezoid. You could lay it on its side, which is how most people like to look at the trapezoid. Okay, but this trapezoid standing on its end, and this is the height. This is base number 1 and base number 2. In these trapezoids, all of the heights are the same. So this is the height, the height, the height, the height, the height, the height, the height. And all of the heights in all of these trapezoid is a common 1. So I'm going to start out my approximation. There's my 1/2. I'm using the geometry formula of a trapezoid. 1/2 of the, in this case, a common height of 1. If the height is not in common, then you have to calculate the area of the trapezoids independently. But all of these trapezoids have a common height. Now, think about the bases for just a second that I just talked about. Let me get rid of this guy right here. I'll redraw. So here's this, this. Now, in the first trapezoid, this is base number 1. This is base number 2. Trapezoid number 1. So we're going to use this base once. And this is base number 2. Now when I go to trapezoid number 2, I'm going to change colors. Here's trapezoid number 2. Now notice what happens. That was base number 2 in trapezoid number 1, but it's base number 1 in trapezoid number 2. Here's base number 2 in trapezoid number 2. Let's go to trapezoid number 3. Base 1, base 2. Let's go to trapezoid 4. base 1, base 2. Let's go to trapezoid. I'm running out of colors here. Let's go to trapezoid 5, base 1, base 2. All right, so I think you're beginning, hopefully you're beginning to get the idea. We're going to go to trapezoid 6, trapezoid 7, trapezoid 8. This last base will only be used one time. The first base is used once. The last base is used once. All of the other bases are used twice. So one simple way to write that up is to remember that I'm going to use the first base once. Now the name of this curve is v of t. So when I write up my trapezoid approximation, I'm going to say that all of this inside the brackets is going to be the sum of the heights, plural, the heights of the trapezoid. So the first base, the very first base, would be v of 0. What does that mean? That means this distance right here. That's how tall the first base is going to be. Now remember what we said, the second base, which is, let's highlight it. I know this is getting to be a mess, so just kind of focus with me. Replay if you need to replay. The second base is used twice. It's used in the first trapezoid and it's used in the second trapezoid. So I'm going to have 2v of 1 plus 2v of 2 plus 2v of 3 plus 2v of 4, I'm running out of space here, plus 2v of 5 plus 2v of 6 plus 2v of 7. Now, careful, I'm on the very last base, which is used only once. So that's plus 1v of 8. All right, so all of the values inside of those brackets represent the sum of the bases. The first base is used once. The last base is used once. All of the other bases are used twice. That's when they have a common height. If they don't have a common height, you just have to calculate the area of each individual trapezoid. So to actually come up with your value, you would look at your graph, you would come up with those approximate y values, add them, do the arithmetic with a calculator, and come up with the distance that Ella traveled in her rocket ship. All right, so now I wasn't paying attention. They suggested that we use 4 trapezoids. We decided to use 8. It doesn't really matter. Again, I said the more the better approximation, but we could have used 4. We could have used more. But the big idea with the trapezoidal rule is that you're just using trapezoids instead of rectangles or counting blocks to approximate a definite integral. So the trapezoidal rule, just as a summary of what we talked about, the trapezoidal rule is used to approximate a definite integral to find the area under a curve. The area of a trapezoid from geometry is 1/2 of the height multiplied by base 1 plus base 2, the sum of the bases. We extend that formula in calculus because we have multiple trapezoids to be b minus a over 2n multiplied by, and this represents, inside the brackets, represents the sum of the bases. Now this formula also assumes a common height. The height is calculated by subtracting the interval b minus a over n, where n is the number of trapezoids. And that will give you your common height. The 2 in your formula, so you can see the b minus a over n right there. The 2 is the 1/2 from the geometry formula for a trapezoid. And then if you take a look at the formula, notice that the first base is used once, as we discussed. The intermediate bases in between are used twice, and the last base is also used once. So that's kind of a summary of what we talked about in the video. All right, let's do one example. Let's take a look at number 1. And instead of using a left endpoint approximation, we're going to use trapezoids. It's just an example. I wouldn't change it on your paper. With 4 subintervals. So we're going to go from 1987 to 1991. So trapezoid number 1, trapezoid number 2, trapezoid number 3. You don't really have to draw trapezoids. You can just section them off. And these are really ugly. So I have my 4 trapezoids. I'm going to approximate that definite integral. Notice that we have a common height of 1, 1, 1, and 1. So the approximation will be the formula for the area of a trapezoid, 1/2 of, in this case, the common height. The first base, 54, is used once. The next base, 74, is used twice. The next base, 107, is used twice. The next base of 86 is used twice. And the last base is used once. Calculate that with your calculator, and you can compare it to when you did that same problem in your homework using rectangles to see how the approximations compare. So that is evaluating a definite integral using the trapezoidal rule.